Hello, I'm Chris Mack, and this is a paper I gave about 2 weeks ago at the SPIE Advanced Lithography Symposium in San Jose, California, called Improvements to the Analytical Linescan Model for SEM Metrology. My co-author is Benjamin Bundy of SUNY Poly Sematech, and the two of us have written 3 papers on this topic over the last couple of years, and this is kind of an update on where we're at in the new work we've done on this topic. As I said, this is a paper I gave about 2 weeks ago, so I'm recording it again, trying to reproduce pretty much the way I gave the paper. Not exactly, obviously, but as much as I can remember the way I gave the paper at the symposium itself. First, the motivation for this work. Why would we want to develop something I call the analytical line scan model? Well, today we measure line scans. We take an SEM, we collect a secondary electron signal called a line scan, and then we measure that to extract the critical dimension, or CD, based on some edge detection algorithm. These edge detection algorithms are fairly empirical in nature. They work fairly well, but they're geared towards precision. That is, getting the same number every time. And they're not really geared towards accuracy. There's systematic biases in the values that come out of these CD measurements compared to what's really on the wafer. And we don't put much effort into trying to reduce these biases. In other words, there are many known physical effects going on that produce these line scans that we're ignoring with our current CD measurement algorithms. One way to deal with this is to rigorously model the measurement process. We could use a Monte Carlo simulator that simulates the way the electrons interact with the sample and predict what these line scans would look like. We're actually going to use one of those kinds of simulators in just a moment, but to do that work on a regular basis, that is for every line scan that we're trying to extract an edge for, would be a very difficult proposition because these Monte Carlo simulators are extremely slow. So we need some middle way, some way of extracting information from the line scan that takes into account as much of the physics as we can, but still enables a real-time analysis of that line scan. And that's what the analytical line scan model is all about. We're going to begin, though, with a more rigorous modeling approach, Monte Carlo simulations. The simulator we're using is called JMONSL. It was developed mostly by John Villarrubia at NIST. It's a first principles SEM simulator, tries to capture as much of the physics of how electrons interact with material that we know about. It's an open source piece of software. It follows electrons as they enter the material, scatter, generate secondary electrons, lose energy, and then backscattered and secondary electrons escaping out might be captured by a secondary electron detector. This produces then the signal, which we call our line scan. We will be mostly using trapezoidal shapes for our features, but with some variations that we'll talk about, and many different materials and beam parameters can be simulated. We're going to use JMONSL as a virtual SEM. We'll perform essentially virtual measurements, and then we'll calibrate the simpler semi-empirical analytical line scan model to these simulated line scans. What we'll ask is, how do the ALM parameters vary with the geometry of and the material properties of the things that are on the wafer in order to create a fully calibrated, very fast analytical line scan model that could predict what JMONSL can predict based on calibrations to JMONSL. Our previous work dealt with silicon substrates, and we had features that were made of either silicon or PMMA. PMMA is a model of a photoresist material. We varied the feature height, sidewall angles, and we had lines and spaces of various pitches and duty cycles over a fairly wide range. All of this work at 500 volts. Well, for the most part. We did a few other voltages as well. What we've done in the work this year is first to add a new material case that is photoresist on top of a bottom antireflective coating. I'm not going to talk about that in this talk. There'll be a separate paper that I gave at that same conference that discussed the calibration of the ALM for the case of resist on a bark. Here we're going to focus on silicon features mostly, but also some SiO2 spacers on silicon wafers. And we're going to add new structure to our trapezoidal feature shapes. We're going to allow the top corner to be rounded, and we're going to allow some footing at the bottom of our feature. And we'll see how that affects the line scan. First, a quick review of the analytical line scan model as it has been published in previous papers. It's physics inspired. It develops the analytical form of the equations based on what we know about the physics of how electrons interact with the material. For example, a beam of electrons would strike a substrate, and as those electrons scatter in that substrate, they might form an energy deposition distribution that looks like a double Gaussian. So we'll model a double Gaussian with a forward scattering and a back scattering length and amounts. And then some of those electrons will escape, secondaries will escape. We'll assume the number of secondaries is in proportion to this double Gaussian energy distribution. And these secondaries can escape and be detected. As the beam scans closer to a feature, some of these, say, backscattered electrons or forward scattered electrons might get absorbed by the step. But some of those electrons coming up into that step might, in fact, escape and be detected by a detector. Or maybe some of the escaped electrons coming out of the surface will be absorbed by the sidewall. As a result, the edge interacts with the electrons as those electrons get closer and closer to the edge, affecting the secondary electron signal. The same kind of phenomenon happens on the top. As electrons get close to the edge, many of those electrons will escape out of the side of the edge, giving rise to the characteristic edge bloom that we see of our line scan. And we have similar kinds of scattering terms when the electrons are at the top of the step. The result is this model for an isolated edge or an isolated step on a wafer. I won't go into the details. All the mathematics are in the paper and have been published previously. In all, there are 11 parameters for this model. Some of them are more important than others when it comes to extracting an edge position. But we're going to use all 11 parameters. One of them is the incident Gaussian beam width. We'll assume the beam of electrons striking the material has a Gaussian shape and a certain sigma p probe width for that beam. And the rest of those parameters, the other 10 parameters, are beam material interaction parameters. Therefore, they depend upon the specific material that our structures are made out of. If we take two edges and bring them together, the edges begin to interact with each other, and we can create features, and so there's some extra parameters related to those interactions as well. Here's an example of both a Monte Carlo simulation of an isolated edge and the analytical line scan model fit to those Monte Carlo simulations. So in the blue, kind of the more squiggly version, is the Monte Carlo results. We've simulated 5,000 electrons per pixel, so there's not a whole lot of noise in our Monte Carlo results. The red smooth curve is the analytical line scan model that was fit to that Monte Carlo result, and you can see it fits essentially perfectly within the noise of the Monte Carlo results. Here I show a couple of pairs of parameters. When the beam is at the top, we have the forward scattering distance, sigma e, and the escape factor, how many of these, what fraction of the electrons escape out of the edge. And as we get closer to the edge, we get a rise in the number of electrons that escape and get to. Then we have two parameters that signal the rounding or the fall off of that rise as I get even closer to the edge. This is the volume loss factor and the volume loss distance. These are just examples of some of the parameters and how they influence the shape of the line scan. All right, so this is all previous work, just a review. Let's look at what we're going to do today. We want to be able to extract a CD. So for example, if I have a perfect trapezoidal feature shown here on the right, it's very easy to define exactly what I would mean by, say, the bottom critical dimension or bottom CD. Likewise, I know exactly where the top CD is because trapezoidal feature has very clear kinks or boundaries at the top and the bottom. That gives rise to a line scan, which also has very clear bottom and top features. These are these very sharp points corresponding to the bottom CD and the top CD. Now, I've simulated an ideal point electron beam with a real beam of electrons that's Gaussian shaped. I would simply convolve this sharp pointed line scan with a Gaussian, and it would smooth it out. Still, it would be very easy to identify where the top CD is and the bottom CD is for this perfect trapezoidal feature. My question, though, is what if the trapezoidal is not perfect? Real-life features often have corner rounding at the top, here, and footing at the bottom. So we're going to add these features to our trapezoid. We'll define a corner rounding radius r and stick a circle or a portion of a circle that goes from the top to the sidewall that rounds the corner and removes the material outside of that circle. And we'll add a foot to the bottom. The way we're going to add a foot is by putting another little trapezoid here. It'll be exactly 2 nanometers tall. We just picked that as a reasonable number. And then we'll vary the width of the foot. So if the foot has a 0 width, that means it is exactly vertical. And then as the width gets wider, it will be wider than 0. We can make this foot go from 1 nanometer to 10 nanometers in length. All of them 2 nanometers tall. And then we're going to ask, what does this do to the line scan? Well, here is a J. Monsell Monte Carlo simulation of an isolated edge with no top corner rounding and no foot. It's 90 degrees, perfectly vertical, and so it's very easy to identify, say, the bottom CD here and the top CD at the peak. Now, let's add a little bit of a foot. I'm going to add only 1 nanometer of footing. So this little extra trapezoid is 1 nanometer wide. And what happens? Well, the minimum point here that corresponds to the bottom of the trapezoid moves over by 1 nanometer. Right? That, I guess, makes some sense. But interestingly, this sharp decline down to that minimum is no longer straight, but is now bent because of that foot. And the position of that minimum is higher than it was before. What if we had a 2.5 nanometer wide foot? We see that this extra structure in our line scan is now 2.5 nanometers wide, and the minimum has become quite tall relative to the prior minimum. In fact, it's starting to become harder to actually identify exactly where the minimum is. If we go to, say, a 5 nanometer wide foot, remember it's still 2 nanometers tall, we see that this edge has moved way out here 5 nanometers away, but because it's grown in intensity, the minimum is now much higher in its line scan signal. It's much harder to identify exactly where that minimum is. And in fact, if we were looking mathematically for a minimum, we might in fact find this minimum over here or over here. They're about the same value. In other words, we can't use the minimum of our line scan as a reliable indicator of the bottom CD. And that's because of the potential for footing. If we have footing, this minimum is moving around and changing its line scan signal value to the point where we're blurring out that minimum and it stops becoming a reliable indicator. What about the impact of top corner rounding? Well, we're going to find out that it blurs the peak. Here I have an example of a 50 nanometer tall feature with an 80-degree sidewall angle. Here would be the bottom CD, and the top CD would correspond to the peak over here. Again, I have an ideal point of electrons striking my feature, and there's no top corner rounding and no footing. Now, what happens if I add a little bit of top corner rounding? Now, 2.5 nanometers corner rounding radius. What do we see happening? We see this decrease in the peak value from here to here. And if I add more, now 5 nanometers of top corner rounding radius, we see that our peak has all but disappeared. In other words, the position of the top CD of a trapezoid gets blurry when I round the top. Well, just like, in fact, if we were looking at a cross-section, we would say the same thing. The position of the top is kind of blurred because of the rounding. And that happens in our line scan as well. And as a result, the peak is not a reliable indicator of top CD due to the possibility of corner rounding. Well, let's try to model these factors. In fact, we'll spend some time looking at the impact of top corner rounding on the ALM. Well, we see a number of phenomena. The first phenomenon we notice is that the peak position is shifting to the left as I add top corner rounding. Well, we can model that in the ALM as a change in the effective height of the resist profile. If we think of our feature as a trapezoid, a somewhat shorter trapezoid behaves a lot like a taller trapezoid with a rounded corner. How much? Well, empirically we find it's the same effect as reducing the height of our trapezoid by the corner rounding radius divided by 1.7. The next thing we see is that the peak value is reduced as I add corner rounding. Well, we can model that by an increase in one of the parameters called the volume loss factor. In fact, we can see these trends for different sidewall angles. The change in this volume loss factor is growing as I add more and more top corner rounding radius, but the amount depends on the sidewall angle. But we can create a little model that accounts for that. And finally, the slope of the inside edge of the edge bloom of my pattern is reduced when I add top corner rounding, and that is an increase both in the forward scatter length and the volume loss range parameters. And here we show how those vary specifically with top corner radius. For the case of the step volume loss range, it's a nice linear behavior with top corner radius and no dependence whatsoever on the sidewall angle. For the case of the step forward scatter range, we have a sidewall dependence to those parameters. But as I add top corner rounding, that sidewall dependence goes away. And if I have over about 3 or 4 or 5 nanometers of top corner radius, then we have essentially a linear dependence on the top corner radius and no dependence on the sidewall angle. If you have enough rounding, this parameter, the forward scatter range, sigma e, is dependent only on the amount of corner rounding and no longer on the sidewall angle. Which tells us something. Where do we want to measure the CD? Well, if we think about this bottom peak as the place where the bottom CD might be measured, if I add a little footing like I show here in the blue, then I lose my ability to use that bottom position as a measure of where that bottom is. If I add corner rounding, the top peak starts to move around and I can't really see where it is. However, this region, this straight sidewall region here, is a stable indicator of the bottom CD. So this lesson, this looking at the Monte Carlo simulation results, teaches us that we probably want to use that straight slope region, maybe extrapolated down to a bottom intensity level, as a measure of the bottom CD. Now, let's apply what we've learned to the case of metrology of sidewall spacer features. In a sidewall spacer feature, we tend to have one side of the feature nearly 90 degrees with a sharp corner, like this, and the other side sloped with a rounded corner. That's kind of the nature of creating a sidewall feature where we etch out the feature after we grow the two sidewalls on either side. So we have an asymmetric feature. Can the ALM handle that? Well, the answer is yes, it can. Here is an example of two sidewall features. The inside parts represent the 90-degree, and then over on the left and the right side, the outside parts here are the rounded corner parts of our line scan. And if I simply take the ALM, an asymmetric version of the ALM, and fit it to this particular line scan, it fits nearly perfectly. Right? There's no problem fitting it. Now, I'm not predicting what that line scan will look like. I'm fitting it. But nonetheless, there's no doubt that the ALM has the capability of handling these asymmetric features. Here's an example of an SiO2 spacer on a silicon wafer. Also, no problem for the ALM to fit these line scan results. All right, so what's my conclusion? We've developed a simple analytical line scan model that so far has matched every rigorous Monte Carlo simulation, at least reasonably well, that we've been able to generate. Various feature sizes, heights, sidewall angles, materials, footing, top corner rounding, and asymmetric features are all well described with this analytical line scan model. And therefore we could use this model for, say, fast prediction of SEM line scans instead of the more rigorous but slow Monte Carlo simulations. And we might be able to use it for the inverse problem. That's our eventual goal. That is, given a line scan, can we extract the feature shape that generated that experimental line scan? There's still a lot of future work to accomplish those goals. We want to continue to expand the range of conditions over which the ALM has been calibrated. Our goal being to make it predictive for any geometry. That is, you tell me the CD, the pitch, the sidewall angle, the corner rounding at the top, the footing, and even asymmetry to the left and right side, and I can then predict what that line scan will look like without having to run the full Monte Carlo simulations. We are not quite there. We're getting close to being able to do that, and I think we'll accomplish that for particular materials at a particular voltage quite soon. Then we want to apply the ALM to experimental line scans and find out how well it might work at extracting feature size, sidewall angle, and other characteristics of the true feature on the wafer given an experimental line scan. Well, that is where we're at to date. I'd like to end this presentation by thanking, of course, my co-author Ben Bundy, but also John Villarubia at NIST, the creator of the JMONSO code, who's been very instrumental in helping us and allowing us to use that code. And it is the basis of all the physical phenomenon that the ALM is based upon. So thank you, John. And thank you for listening.